Hello, my name is Pawel Gomoluch and this presentation is about learning neural search policies for classical planning. This was a part of my PhD and this is joint work with my supervisors Alessandra and Dalal at Imperial and Antonio at FBK. We are working in the setting of satisfying classical planning, which we approach as a heuristic forward search problem. Within that setting, we would like to build a planner which does not rely on a single fixed search routine, but instead it can adapt its search approach based on the current situation. For example, it might switch from global to local search in the face of a plateau of the heuristic function, or when it is running out of time. Furthermore, we would like such search policies to be learned automatically to optimize for a given problem distribution and performance objective. We have tackled a similar problem in our paper presented at ICAPS last year. That approach was based on a discrete action space. The planner was equipped with a number of fixed search routines, such as best first search, random walks, local search, and so on. And it would choose a routine and then keep applying it for a preset period of time, after which it would choose again, and so on. While simple and effective, this approach came with a number of limitations. First, there was a lot of fixed hyperparameters, such as the epsilon for epsilon greedy search and the length of the time step. Intuitively, having to set values of such hyperparameters is very much at odds with the idea of having a learning planner. We would really prefer it to find such values on its own. Further, operating with a number of fixed routines imposed somewhat arbitrary restrictions on the policy space. So, for example, you could choose between randomized and local search, but you couldn't combine them. To address these problems, this year we introduced a solution based on a continuous action space. Instead of having a set of fixed routines, the planner operates with a single parametrized search routine whose effective behavior depends on the values of the parameters. For specific values of the parameters, the routine can assume any of the search techniques on its own. And for intermediate values of the parameters, it can combine elements of various techniques. The general idea behind the parametrized search routine is to interleave between a number of global and local node expansions. Every call of the routine starts with a number of global expansions, followed by setting up a new local open list, which is then used for a number of local expansions. Both the global and the local phase can optionally randomize the order of node expansions or follow the expansions with random walks. Overall, the parametrized search routine comes with the following parameters. There is the epsilon for epsilon greedy search. There's the condition for triggering random walks, the number of node expansions without progress. There's the number of random walks following a single node expansion, the length of each of the walks, and also the total number of expansions performed within a single application of the routine, and the proportion of local expansions within that total number. In general, we would like our search policies to set the values of the parametrized search routines parameters based on the current state of the search. Towards this goal, we consider a number of high-level variables characterizing the progress of the search, such as the initial value of the heuristic, the lowest observed heuristic value, h-mean, the number of node expansions since this value last changed, and also the time elapsed since the search started. Note that since we always run the search with a fixed timeout, the latter also implicitly encodes how much time there is left. We evaluate two variants of the approach. The first one is a full state-dependent setting, where we use a feed-forward neural network to map the statistics of the search to the values of the routine's parameters, and in this way adjust these parameters on the go. The second variant is an ablation of this state dependency, in which we learn the values of the routine's parameters directly, without regard to the state of the search, and we keep these values fixed throughout the search and across problems. We train our approach using the Cross-Entropy method, which is an instance of a broader class of evolution strategies. The general idea here is to introduce a distribution over possible solutions and to iteratively update the distribution with the general objective of maximizing the likelihood of observing those solutions which empirically have performed better. This is what training of a planner looks like in practice. We start with a normal distribution over the search policies, parametrized by mu and sigma. At every iteration of the main training loop, we sample a number of problems. The problems don't generally have to be identically distributed, and in particular, in our experiments, we sample sequences of problems of increasing size, just like the ones used in IPC. We then sample a number of search policies from the current Gaussian distribution over the policies. And then we essentially put the policies in an IPC-like competition against each other. So we run each of the policies on each of the problems, and we compute their aggregate IPC scores to pick the m best performing ones. The mean and covariance of the distribution are then updated towards the mean and covariance of the best performing policies. After a number of iterations, the result is the mean of the final policy distribution. We evaluate our approach on 5 domains from the learning track of the IPC. We use the problem generators provided by the organizers and the range of problem sizes as in the satisficing track of IPC 2011, along with a timeout of 3 minutes. And here are the results. The table shows IPC scores achieved on held out test problems generated in the same way as the training ones. And these are averages over 10 such sets per domain. We compare against search algorithms corresponding to our constituent search techniques on their own. These are greedy best first search, epsilon greedy search with random walks, and local search. Then mixed is an instance of our parametrized search routine where we set all the parameters manually to make a balanced use of all the search techniques. Opt is the stateless variant of our approach, where we use our training loop to optimize the search parameters directly. And finally, NSP is our full state-dependent neural search policy, trained separately for each of the domains. The learned variants generally performed well, especially relative to the mixed variant, which suggests that their strength comes from the optimization, rather than simply throwing all these techniques together. Among the two learners, there is a benefit of state dependence clearly manifested in the elevators domain. On the other hand, there are also cases where the stateless variant performs better. This is slightly surprising, given that NSPs are strictly more expressive. We believe that this effect is due to the fact that, given the computational resources, the variant with much less parameters is much easier to optimize. This effect, and more generally improving the optimization procedure, is certainly something we are going to investigate in future work, along with possible extensions of the parametrized search routine, as well as more complex representations of the planner's state. So to sum up the contributions of this work, we have introduced a parametrized search routine combining elements of various search techniques, a search policy model which sets the values of the routine's parameters based on the state of the search, and an evolutionary training scheme based on the cross-entropy method. Thank you.